Welcome to Mathematics with Tom. I am Tom, and today we are going to take a look at, this is section 4.2 in our text, and it's called projections. It's called projections. So the first thing we're going to do is we're going to just explain what a projection is, and then we're going to look at a little bit more advanced idea of a projection, and then we're going to see why we need these. So here we go. Let's take a look at this. So I'm going to have two vectors here. This is the vector, we'll call it B, and then I'll have a vector here. It doesn't really matter. It's usually easier pictorially to make it long, so A. Those are vectors. Now the projection, this is what we call it. We call the projection P of B onto A. And here's what it is. So what we are going to do is we're going to drop a vertical line, not a vertical line, but a line perpendicular from B onto A. So I'm going to add this, and let's do this in another color to help keep track. This vector right there, okay? That is my projection. No, I'm sorry, that's not the projection. The projection, though, the projection is right here. It's this pink vector, P. That is the projection of B onto A. And I'm going to label that it is P. But notice something else about P. P is the same as the vector A multiplied by some scalar. Or we could write it as the scalar times the vector A. Either one is fine. Now, another thing comes up, and that is the vertical line the line that is perpendicular from B onto A. We call this vector E. We're going to call it E for error. And if we give it some kind of a direction, maybe we'll make it going up towards B, then E is B minus P. Okay? Now, here's what we know. We know that the vector E, let's keep track of this. We know that E is perpendicular to A. All right, that's what we know for sure. Well, if it's perpendicular, and we can write it either way. I'm going to write it this way. Then we know that A transposed, I'm going to write it like this, sorry. We know that it's perpendicular to A. So what we know is that if you take A transpose and you multiply it by E, you're going to get 0. That's what it means if those vectors are orthogonal. So let's continue this idea out. So A transpose E is A transpose times E. Well, E is B minus P. But we know a little bit more. This is A transpose times B. But P we just said is A times some scalar x. Well, this is equal to A transposed B minus A transpose A x. Okay, let's see, I'm going to have to come up here, so I'm running a little short on room down there. I'm going to just move those over to solve this. So now I have, what do I get? I have that A transpose A x is equal to A transpose B. Now let's just go one more step, because if we know what x is, if we look back at what we were up to here, if we know what x is, well then we know P. So let's solve for x. So I'm just going to take this crazy step. I'm just going to say x is equal to A transpose B divided by A transpose A. And at that point right there, you should immediately begin to feel a bit uncomfortable. And so let me explain why. My question to you is this. can I just simply divide by A transpose A? Can we just divide by A transpose A? The answer is yes. That was legitimate. Yes. And why is that? Well, A transpose times A. Remember, that's just A dotted with A. You could write it that way if you wanted. Well, what is A dotted with A? It's just a scalar. In other words, A dotted with A is just some real number. That's all it is. It could be a 5, and we've divided by 5 plenty of times in our courses of algebra over time, so maybe we're just dividing by 5. So that is completely legal. But you should always ask yourself these things because these are vectors, and you have to think of what form they're in as you go. Okay, let's plug this back in. We said that P is equal to A times X. Well, X is A transpose B over A transpose A. And then I'm going to rewrite this a little bit. I'm going to reorganize this as A transpose over A transpose A, and then I'm going to multiply by B. Wait a minute. Then I'm going to rewrite this as capital P times B, and you can see where capital P is A transpose over A transpose A, and is called the projection matrix. It's called the projection matrix. Okay, let's try an example. Let's try a simple example here. So what about, we're going to project B, and B is 1, 2, 2. B is 1, 2, 2. Onto A. And A is the vector of 1, 1, 1. All right, let's try this. Let's see what happens. Well, let's first calculate P. So P is A transpose over A transpose A. So you know what? Let's do this. Let's first find what is A transpose. Well, that's A. A is 1, 1, 1 times A transpose. Well, this is going to be 1, 1, 1. Well, that's just going to give us the 3 by 3 matrix. Well, remember, of a row times a column, that's a 1, and you continue that, and you're going to get 1s. That's it. That. And then, what else do we have here that we have a little bit more? We also have, that A transpose A, comma, is equal to A transpose, that's 1, 1, 1, times A, which is 1, 1, 1. That is going to give us 3. Okay, so here's what we've got. So we can say then that P is equal to 1/3 times this big matrix here. I'm going to have to make it small to fit it in here. 1, 1, 1, 1, 1, 1, 1 times B. Well, B is 1, 2, 2. So this is going to be 1 times 1 plus 2. That's 3 plus another 2 is 5, and then it just repeats. It's 5, 5, 5 times 1/3. In other words, it's the vector of 5/3, 5/3, 5/3. Okay, and that is how you would project B onto A. Okay. Oh, and notice this. Here's what I wanted to write it this way. Notice that if I take and wrote this as 5/3 times 1, 1, 1. Well, what is that? Well, that's just 5/3 times a, which is what we said. We said that the projection of b onto a would simply be the vector a times a scalar. And in this case, the scalar is 5/3. Okay, so now, you ready? We're going to go to the second page. And on that page, we are going to take the projection onto a plane. So, and actually, you know what? I think we'll just stop this video here and we'll do that in the next video. So, hope that helps. Thanks for watching.